Hello everyone, welcome to this tutorial on wideband envelope tracking. Wideband envelope tracking is very important because signals are getting very high peak to average power ratio and high peak to average power ratio as well as very wide bandwidths, and these bandwidths can range from 50 megahertz to even 1 gigahertz in 5G and in the forthcoming 6G systems as well. So broadband, linear and efficient amplification is the key challenge and a very sought after goal in industry right now, and many companies are rushing to find solutions to have broadband efficient linear amplification. Envelope tracking is one such technology which has a potential to overcome this problem, and it is again highly sought after technology in industries like Qualcomm, and many other companies are working in improving their envelope tracking system and even designing new systems. So the linear amplifier used in the split stage ET system is the most important block whose design affects the bandwidth. As we are talking about the bandwidth, so we will focus on one particular type of envelope tracking system, which is the split stage ET system. And in that system, there is a component known as a linear amplifier. So the design of that linear amplifier is ultimately responsible for the bandwidth. In case you are not familiar with envelope tracking or the split stage ET, I would recommend you please go into our earlier videos in which we talk about envelope tracking in more details as well as what the split stage ET system means. So please go into those videos, because in this video we will only talk about the op-amp topologies which are used in the linear amplifier, which again is a part of a split stage ET system. So the op-amp topologies which are very much discussed and found in literature are the two major topologies used in the linear amplifiers in split stage ET system, and those are folded cascade op-amp or folded cascade OTA with class AB output stage. The reason you might be aware from your analog circuit design that the OTA with an output stage is an op-amp, so we can call it an folded cascade op-amp as well. And the second is the source coupled OTA with class AB output stage. So these two topologies are very important topologies when it comes to the linear amplifier design in split stage ET system. When we talk about op-amp, every op-amp can be divided basically into three major sections, and those sections include the input stage, which is mainly for amplification. Then comes the intermediate stage, which is for isolation. It can also provide some gain as well. And thirdly is the power stage, which is the output stage. So amplification, isolation, and then the power stage. Usually the power stage is class AB, is made in class AB mode, but other modes are also possible. But usually we find in literature regarding the wideband ET system that they use class AB output biasing. And also for every op-amp we must have RC compensation or of some form or the other to stabilize the op-amp, and also this has a bad effect that it reduces the gain bandwidth, but we have to do it. So let's get started with the topologies of the op-amp used in this wideband ET systems. And the first one which we'll be talk about is the folded cascade. We'll talk about is the folded cascade op-amp, and you must know from your analog design course that this op-amp uses complementary transistors, i.e. one stage is one part is the PMOS device, other part is NMOS device. For example, here in this diagram, the common source part is the PMOS, is made up of PMOS devices, and the common gate part is made of NMOS devices. And the benefit of using folded cascade is that it does not have the problem of stacking. For example, in normal cascade we have to have a lot of stacking, and it is not it is very challenging in low voltage supplies to achieve good gain with stacking, because a person runs out of the headroom. So folded cascade has this benefit that it does not have the stacking issue. And again, yeah, there is some power penalty one have to pay because both devices are biased with separate current sources, but with good design a folded cascade is a very optimum topology. And here this stage, as we see, these devices are the common these devices are common drain devices. This is acts as the intermediate stage, and these devices are used for biasing. It's very clear from this diagram. And this is for the compensation. These RC components here, and these C and L represents the power amplifier, because the power amplifier is connected to this op-amp in the linear amplifier, which is a part of the split stage ET system. So this is just modeling the power amplifier part, and this is the feedback resistance. You can ignore these for the moment, but this is the main folded cascade architecture. Similarly, the next folded cascade architecture is also very similar with some differences as compared to the previous one. Here we have rail-to-rail folded cascade op-amp. It has the NMOS pair, PMOS pair, and then again it has the complementary common gate pair as well. So it's a rail-to-rail folded cascade op-amp. Other than that, there is not much difference between this one and the previous one. So now we come to the third folded cascade op-amp. It is also not much different from the other two, except the biasing scheme in the class AB output stage, and other than that it's very close to the second one. So the main thing is that folded cascade is one of the basic topologies which is used in linear amplifier for split stage ET system and for wideband linear amplification. The third topology of op-amp which we will talk about is a source coupled op-amp. This topology is basically common drain amplifier with the common gate amplifier, and this works that when the signals come here, so we have a conductance path from this node to this node, and then the current is mirrored to this intermediate stage, and then it is delivered to this class AB output stage. And these devices, if you are any confusion about it, these are just acting as resistors to provide variable gain if needed. So one can bias this differently to provide a variable gain to this common source amplifier and change the biasing conditions at this node. So essentially what we have seen is we have seen two major categories of op-amps. One is the folded cascade op-amp with some variations, and other is a source coupled op-amp. So when people are designing this, we cannot say whether folded cascade is better or source coupled is. One has to design both of them or all the variants of them, and have to check them in their technology which one is better. One has to check them for their power consumption, slew rate, bandwidth, CMRR, common mode rejection ratio, that is power supply rejection ratio, gain, bandwidth, product, stability, and all the parameters. So but these are the two major topologies which are being used and investigated by many perhaps companies and also in academia as well. So as I said, that ET is a very complex analog RF mixed signal system. It is very, very difficult to simulate and correctly characterize it. So one have to measure it in the lab, and then with a lot of experimentation one can learn about this complex system. But again, it's a very, very valuable system. It's hotly pursued for 5G and definitely for 6G communication system as well. And the long-term behavior is challenging because of memory effects. And then if one want to characterize, as I said, he has to design this in the lab and check it. So in this video what we saw the two major topologies for the op-amp using wideband ET systems. These are folded cascade and source coupled. There might be other as well, so we will maybe discuss in other videos if we find some other. So that's all. So and please see other videos of ET and power amplifier which are posted in this channel, and don't forget to visit our website, which is www.poweramplifier.net. Don't forget to read the description, as we might update if some update is there or if anything changes. Thank you very much.